Okay, so welcome everybody to the thematic session in Dynamical Systems of the 33rd Brazilian Colloquium of Mathematics, 33º Colóquio Brasileiro de Matemática. And we are going to have 8 speakers that are divided into 2 days. The first day is today. We're going to have 4 of them. And then next Thursday, at the same time, starting at 2:30 p.m. here in Brazil time, we're going to have the next 4 speakers. And before proceeding to some announcements, I would like to give the word to Ali, who will say a few words regarding the Brazilian Colloquium of Mathematics.
Okay. Thank you very much, Yuri. Thank you very much, colleagues, Karina, Yuri, in this organization. So first of all, in the name of all organizers, Yuri and Karina, I would like also to welcome you all in this Zoom section or people who are in YouTube to this dynamical system sections of Brazilian Mathematical Colloquium. So in few minutes, I would like to mention some things about the colloquium. So the Brazilian Colloquium, Mathematical Colloquium, is a traditional event, biannually realized, and it includes almost all areas of the mathematics. So in fact, it began in 1957 at Poços de Caldas. It is a city in the state of Minas Gerais, under the auspice of CNPq, and up to 85, it means 15 editions of colloquium was realized at Poços de Caldas, a very long period. And in this long period, almost, and the period of colloquium was almost 2 or 3 weeks in the beginning editions. So it changed really the history of the life and academic career of many known professional mathematicians in Brazil, if not foreigner also. It had always the support of CNPq, among other federal and state agencies in Brazil. So while in the first edition, it had more or less 50 participants, after 9 edition in 73, it had almost 600 participants. So it grows really very exponentially. And this 9th edition in 73 was exactly the edition where the special sections began to exist. So one of these special sections is dynamical systems. Today we have 20 sections, 20 special sections. So in the first special sections of dynamics, you may see the name of Mauricio Peixoto, Jorge Sotomayor, Anthony Manning, among others. And there are many very great names during these periods. So from 85, all of the editions had been then realized at IMPA, Rio de Janeiro, and the number of participants were well above 1,000 of participants. So there are very great names in this history, and you may find the growth in terms of numbers of institutions and variety of mathematics in all of these editions. So finally, we hope really that this beautiful event, which contains the DNA of Brazilian mathematics and its foreigner collaborators, can be realized again, at least at some level in person in 2023. And maybe more importantly, science and in particular mathematics gets its deserved value by institutions and governments. So thank you very much. Yuri.
Thank you, Ali. So now I'm just going to make a few announcements regarding some events that are going to happen in dynamics now in the 2nd semester. So you might be seeing my window here. So one of the events is actually co-organized by Karina Marin, who is also one of the organizers of this thematic session, is the Encontro Virtual Mineiro de Sistemas Dinâmicos. So you can find more information here on the official website. And especially you can register. So the event is going to happen actually 2 weeks from now, a little bit more than 2 weeks from now. The second event that I want to point out to you is the Brazilian School of Dynamical Systems. So it's also something that started only a few years ago. I think the first one was in 2010 or 2012. I don't recall it very much. We are now in the 6th edition. It was supposed to happen in person here in Fortaleza at the Universidade Federal do Ceará, but we are still gonna do it in a remote mode, so 100% online, and it will be dedicated to the 60-year birthday of Lorenzo Diaz. So in this website, you can also register here and see the list of mini courses that are going to be offered, and also of all the speakers. And finally, we have this event that we just started saying about it last week. It's called Markov Partitions and Young Towers in Dynamics, and it's organized by José Alves, who is one of the speakers at this session here, myself and Stefano Lusato, which is a professor at ICTP. And the idea is to gather together the techniques of Markov partitions and Young Towers, and so that people from one side can learn from in the other side as well. Okay, so you can also enter in this link here and register for the event, which will start in the second half of November. Okay, so now I'll stop sharing and Omri can start sharing, and then I'm going to present him. Okay, very good. So I have I'm very happy to introduce Omri Sarig, who is the first speaker of this thematic session. Omri was a PhD student of John Aronson at Tel Aviv University, and he has won many prizes in his professional career. Among them, I'm going to cite actually only 3. One of them is that he gave an ICM talk, the thematic session of dynamical systems, at ICM 2010. And in 2013, he won 2 very influential prizes, the Erdős Prize and the Brin Prize, which is the prize dedicated to the best work in dynamical systems and ergodic theory that occurs at the moment. So welcome Omri, who is going to be speaking about discontinuity of Lyapunov exponents for surface diffeomorphisms. I think you are muted, Omri. Oh, actually, no, but can you hear him?
I don't think that I'm muted.
Now we hear you.
Now you hear me. Okay, good.
Yes, sure.
Can you hear me well?
Yes.
Okay, good. So let me thank you, Yuri, again, Ali and Karina, for the invitation to come and speak at this meeting. I'm going to tell you about a joint work with Sylvain Courvoisier and Jérôme Bouzy on continuity and discontinuity properties of Lyapunov exponents for surface diffeomorphisms. So here are my collaborators. This is Jérôme Bouzy and this is Sylvain Courvoisier. The setup is going to be as follows. We will be working with diffeomorphisms acting on surfaces. Dimension 2 is going to be essential to everything that I'm going to say. The diffeomorphism will always be very, very smooth. In fact, throughout this talk, it will be C infinity. We will be interested in sequences of ergodic invariant probability measures, and more precisely, their Lyapunov exponents. Since we're in dimension 2, there are going to be 2 Lyapunov exponents. The maximal one will denote by lambda plus, and the minimal one will denote by lambda minus. Now, it is a well-known fact that the Lyapunov exponent is not a continuous function of the measure in the weak star topology. That is to say, you could have sequences of ergodic measures mu(n), which converge weak star to an ergodic limit mu, but in such a way that the Lyapunov exponents do not converge to what they should. And this was a big problem for Sylvain, Jérôme, and I in a project we were working on. And we really wanted to know which additional condition should we check on a sequence of ergodic invariant measures to know that its Lyapunov exponents converge to the Lyapunov exponents of its limit. And what this talk is about is exactly the search for such a condition. And here is our result, first in a qualitative form. If you assume that the diffeomorphism is C infinity smooth and that the manifold has dimension 2, then what you need to know, in addition to the convergence of the measure mu(n) to the limit mu, you need to know that the entropy converges to the entropy of the limit, and you need to know that the entropy of the limit is positive. If you know these 2 additional conditions, then it does indeed follow from the weak star convergence of mu(n) to mu that the Lyapunov exponents of mu(n) converge to the Lyapunov exponents of mu. Okay, so the answer to the question which additional condition should one check is written in red here. Okay, Now, this is the qualitative version of our result. There is also a quantitative version, which I would like to present now, and it is an inequality. So before the inequality, the setup is exactly as before. We have a C-infinity diffeomorphism acting on a surface, and we have a sequence of ergodic invariant measures, mu n, which converge to an ergodic invariant limit mu. And let's assume, without loss of generality, that the entropies of mu n converge to a limit, and that the Lyapunov exponents of mu n converge to a limit. We can always pass to a subsequence, so this is true. And then the statement is this inequality. So let's read this together. Let's start with this expression here. So this is the ratio of the Lyapunov exponent of mu n and the Lyapunov exponent of the limit of mu n. If this ratio is equal to 1, then it means that the Lyapunov exponents of mu n converge to what they should, and we are very happy. If this ratio is not equal to 1, then it means that there is some discontinuity. And the further this ratio is from 1, the bigger is the discontinuity. Similarly, we have a discontinuity ratio for the entropy. This is the ratio of the limit of the entropies of mu n and the entropy of the limit of mu n. If this ratio is equal to 1, it means that we have continuity along the sequence. If this ratio is not equal to 1, it means that there is a discontinuity. The entropy of the limit is not the limit of the entropies of mu n. And the further this ratio is from 1, the bigger is the discontinuity. Now, you will notice that both discontinuity ratios are less than or equal to 1. This is an upper semi-continuity statement, which says that the discontinuity can only go in a certain direction. The Lyapunov exponent of the limit is always bigger than or equal to the limit of the Lyapunov exponents of mu, and similarly for the entropies. Now, this is not our result. This was known before. The upper semi-continuity for the top Lyapunov exponent in our scenario is an exercise. It's not a difficult thing. The upper semi-continuity of the entropy is a very difficult thing. It's a house, and it already uses the full force of the C-infinity assumption. Now, our contribution is the middle inequality, which says that the discontinuity ratio of the entropy is always at least as far from 1 as the discontinuity ratio of the Lyapunov exponent. This means, in some sense, that the Lyapunov exponent is more continuous, more continuous than the entropy, or less discontinuous than the entropy. The jump is smaller. In particular, if somebody tells you that the entropy of the sequence mu n converges to the entropy of the limit of the sequence, then this discontinuity ratio is equal to 1. This here, the upper bound is also 1 by upper semi-continuity, so it follows that this must be equal to 1 because of the sandwich, okay? So you get that the continuity of the entropy, so that is to say that if the limit of the entropy of mu n is equal to the entropy of the limit of mu n, then necessarily the limit of the Lyapunov exponent of mu n is the Lyapunov exponent of the limit of mu n, okay? So this is why we get this qualitative result, which I mentioned before. If on top of knowing the convergence of the measures, we also know that the entropies converge, then it follows that the Lyapunov exponents converge. Okay, so this is the result. Now the rest of the talk is going to be a sketch of the proof. So if there are any questions on the statement, then now is a good time. Unfortunately, I can't see YouTube and I can't see the chat of the Zoom. So if there are questions in chat, please let me know. Is it okay?
Sure. Yes, it's okay.
Okay. So can I continue?
Yes.
No questions. Okay. So let's move to the proof. But the proof has 3 steps. The first step, we define a certain parameter, which I'm going to call the density of neutral blocks. I will explain what this means later. It's a number, which is associated to the sequence of measures. The second step of the proof is to show that this number exactly calculates the defect in continuity of the Lyapunov exponent. And the third part of the proof is shows that this number beta gives an upper bound for the defect in continuity of the entropy. So 2 and 3 imply the result because 3 implies that the discontinuity ratio of the entropy is less than 1 minus beta. And 2 implies that the discontinuity ratio of the Lyapunov exponents is bigger than or equal, or in fact equal to 1 minus beta. So you get that this is less than or equal from that. Okay, so there are 3 steps of the proof. And what I'm going to do next is just say a few words about the proof of each of these steps. So I'm going to start with the first step, which is the definition of this number beta. Okay, let me start with some notation. So we are in dimension 2, and we are assuming that the entropy of the limiting measure mu is positive. This means that there are two Lyapunov exponents, one positive and one negative. This is a consequence of Welles inequality. Because there are two Lyapunov exponents and we are in dimension 2, it means that in the oscillated decomposition, the oscillated spaces which are associated to the Lyapunov exponents are both one-dimensional. Okay, I'm going to denote by E minus the oscillated space associated to the minimal Lyapunov exponent, which is negative, and I'm going to call E plus the oscillated space which is associated to lambda plus the maximal Lyapunov exponent, which is positive. The Lyapunov exponents themselves are, of course, the exponential rate of growth of vectors in the right oscillated space under the action of the transformation. So now there is, because we are in a case when the oscillated spaces are one-dimensional, it is possible to write the Lyapunov exponent as the limit of ergodic averages. This is well known, but because I'm going to use it all the time, let me just briefly recall why this is the case, mostly to fix notation. So let's play with the top Lyapunov exponent. This is by definition the exponential rate of growth of the derivative on E plus. Now by the chain rule, I can expand the derivative of Fn into the product of these derivatives. Because I'm only required to evaluate the derivative on E plus, and because of the invariance property of the oscillated spaces, it is enough to consider the restriction of the derivatives to the one-dimensional spaces E plus of x, E plus of f of x, and so on. Now this is a good thing to do because since these are one-dimensional spaces, the derivative acts like a scalar. Okay, it's a linear operator in a one-dimensional space. It acts like a scalar, and because of this, the norm of the product is the product of the norms. I apply the log, and I get this expression as a limit of Birkhoff averages. Okay, so remember this, that you can express the Lyapunov exponent as a limit of Birkhoff averages because I'm going to use it all the time. Okay, so here is a graphical representation of what I just said. What you have here is the graph of this function, okay? The logarithm of the derivative of f to the power n restricted to E plus, okay? I express this as a Birkhoff sum. And here is a graph of this Birkhoff sum, at least the dependence of this Birkhoff sum on the parameter n. The x-axis is n, and the y-axis is the value of the Birkhoff sum. Now, because of what I just said, the Lyapunov exponent is going to be the asymptotic slope of this graph, okay? Because it's the limit of the Birkhoff averages when you divide by n. So it's the asymptotic slope. Of course, the asymptotic slope describes what happens eventually asymptotically, but locally you can see different types of behavior. For example, if you start looking at what happens beginning at this time, and you look at the slopes, okay, of the accumulated derivative starting at this time, well, you see that what you see is not growth at the rate of lambda. Actually, what you see is decay, okay? And this lasts a certain amount. Let's stop following what happens before we go beyond the threshold of a slope of delta. So during this time period, starting from this point, what I see is not a positive slope lambda. What I see are negative slopes, or at least slopes not exceeding a certain parameter delta. Of course, this can only happen finite amount of time because eventually I'm going to see the asymptotic result, which is the true result, which is this slope lambda. But temporarily, I can see something else. So I'm going to call such blocks of time, finite blocks of times, neutral blocks. I'm going to call them delta neutral blocks if I want to emphasize the fact that I never exceed a certain threshold slope, which is delta, a small positive number. Here is another delta neutral block, okay? Here is the formal definition of a neutral block. A neutral block is a finite piece of orbit along which what you see is exponential growth of at most rate delta. That is, of course, not what you see eventually. Asymptotically, what you see is asymptotic growth at the rate of lambda, okay? But for a finite amount of time, you may see something different. And if you do, then we speak of having a delta neutral block. So this is exactly, this definition is exactly what corresponds graphically to this picture, okay? So now here is my informal definition of this number beta here. suppose you have a sequence of ergodic measures mu I, which converges to an ergodic limit mu. We are going to define, maybe for a subsequence, beta to be the density of very long delta neutral blocks for typical points with respect to mu I in the limit as I tends to infinity. Okay, let me say this again. Beta is informally going to be the density of very long delta neutral blocks along typical orbits of mu I in the limit as I tends to infinity. Of course, there are many other limits that I'm hiding in the statement. There is the limit as delta tends to 0. There is the limit as the length of the block we look at tends to infinity. And there is the limit which gives you the asymptotic density along a typical orbit. Of course, there is also the limit as the index of the measure tends to infinity. Now, the order by which you take these limits matters. It is really important, and I will tell you what it is in the next transparency. But I would like you to think of beta informally as nothing other than this: density of very long neutral blocks for typical points with respect to mu I as I tends to infinity. Now let me tell you what is the formal definition. That is to say, let me tell you exactly formally what is the order by which you need to take all the limits in the definition of beta. So again, we assume that we have a sequence of ergodic invariant measures mu I, which converge to an ergodic invariant measure mu. And for each mu I, let's fix a typical point, xi. What exactly does typical mean? I will tell you later. It's going to be some condition which holds almost surely with respect to mu I. Okay? So now let's fix a typical point, xi, for this measure mu I. And let's look along this orbit at all the delta neutral blocks with length more than L. Okay, so there is it's a family of time periods, and let's look at their union. Okay, so beta is going to be this iterated limit. Okay, it's going to be this iterated limit, and this is a complicated formula. So let's read it together again, starting from the inside. So let's start from what's written in the brackets. Okay, so newt delta L of xik is the union of all delta neutral blocks of length at least L in the orbit of xik. We are intersecting this collection of times with the interval 0n and dividing by n. This gives us the density of times which are inside neutral blocks up to time n. And then we pass to the limit as n tends to infinity. Here I'm going to use the assumption that xi is typical. If xi is typical, then the limit as n tends to infinity exists. This is basically because of Birkhoff's ergodic theorem. So for almost every choice of initial condition, we will have an asymptotic limit here as n tends to infinity. What we obtain is a quantity between 0 and 1, which of course depends on the measure. That is to say, depends on the index of the measure that we are using. Now we would like to send the index of the measure to infinity. But of course, without any additional information on the sequence of measures, there is no reason to assume that the sequence of densities that we get converges to something. What is certain is that it's a sequence of numbers between 0 and 1, and therefore there exists a subsequence along which the limit of densities exists. So let's choose such a subsequence so that the limit of densities exists as the index of the measure tends to infinity. Then this limit exists. Now we get a number. This number still depends on delta and L. The last step is to send L to infinity and delta to 0. Why does this limit exist? Basically because of monotonicity. When I increase L and decrease delta, I decrease the number of relevant neutral blocks which enter into this collection. Therefore, I decrease the density. So when L tends to infinity, when L increases and delta decreases, this density here decreases monotonically, and therefore there is also a limit as L tends to infinity and delta tends to 0, and this last limit is going to be this parameter beta, which I defined informally before as the density of long delta neutral blocks for the measures mu I as I tends to infinity. Okay, so this is the formal definition.
Can I make a quick question?
Yes.
So do you first take the limit in delta or in L or in both?
It doesn't matter. It doesn't matter. Because of monotonicity, all regimes of passing to the limit will give the same result. Mm-hmm. But you are right. This is something that we need to check. Other questions?
Yes. Does this value depend on the subsequence you get?
Yes.
Okay.
Yes. Yes, it does. Other questions? I'd like to say that this is a very good question. In the theorem, I made an assumption that the limit of the Lyapunov exponents of mu n converges, exists. Okay, that it's not a lim sup, it's a real limit. This, once you make this assumption, then eventually you see that beta does not depend on the subsequence. But if you do not make an assumption that the Lyapunov exponents of mu n converges, then different subsequences will have different betas. So this is actually a very good comment. Other questions?
Omri, we have some other questions, but I'm going to leave them for the end, okay?
Okay. So let me move to the second step. The second step says that this beta, as we defined it, exactly calculates the discontinuity ratio of the top Lyapunov exponent. That is to say, the discontinuity ratio of the Lyapunov exponent, which is this divided by this, is 1 minus beta. Okay, so let's return to this picture, which expresses the Lyapunov exponent as the asymptotic slope of the graph of these Birkhoff sums. So what is the asymptotic slope? Well, it's the limit of slopes in finite times. This is, of course, the ratio of the vertical displacement divided by the horizontal displacement. Now, if you think about it, you see that whatever happens inside delta neutral blocks doesn't really affect the vertical displacement, because once you leave the neutral block, things more or less cancel out. So when you calculate the vertical displacement, you don't need to worry about what happens inside delta neutral blocks. You will get more or less the same vertical displacement. Whatever happens inside a neutral block almost cancels out when you exit it. So to summarize, the delta neutral blocks do not affect the vertical displacement, but notice that they do certainly affect the horizontal displacement. They waste time. Okay, so this is the important picture that I would like you to keep in mind. It leads to the following approximation. Suppose we fix the index n and we look at the Lyapunov exponents of mu n. We know that this is the limit of the Birkhoff averages. But because whatever happens inside delta neutral blocks doesn't matter, we can remove from this Birkhoff sum the terms which fall inside the delta neutral blocks, because they almost cancel out. What you obtain is an approximate formula for the top Lyapunov exponent as the average of the Birkhoff sums without the delta neutral blocks. There is some error term, but this error term will go to 0 as delta tends to 0 and L tends to infinity. So
can I make a question? Can I make a question before you go to the main technical step?
Yeah.
It's a question from Enrique Pujals. He's attending the talk through YouTube, and he sent the following question: how are the neutral blocks related to hyperbolic times, or Pliss time, which are also known as Pliss times?
You obtain them from the Pliss lemma. They are intimately connected to hyperbolic times.
Okay.
Intimately related. Maybe I will say more on this at the question time. Okay, so we want to calculate this this limit, and in order to do this, what we do is we replace the limit, the average of numbers, by an empirical measure. That is to say, we view this sum as the integral of the function log of df restricted to E plus on a certain atomic measure, and this is the atomic measure. Okay, for reasons of convenience, I would like to express this atomic measure as an atomic measure on the projective bundle. That is to say, the collection of pairs of points and directions. And then I need to evaluate with respect to this measure, the integral of the function log of the restriction of the derivative to a direction. Okay, and this will exactly give me this number. Now, the technical step says that the limit of these empirical measures is 1 minus beta times the lift of the limiting measure to the graph of the topo-selected space. I'm a little bit running out of time, so I will not explain how to obtain this limit. I will just tell you why there is a 1 minus beta here. It's very easy. It's simply because the total mass of this measure is the total mass of this measure. If you calculate the total mass of this measure, you will exactly get 1 minus the limit we had before in the definition of beta. So this is why 1 minus beta appears here. Why the limiting measure is the lift to the graph of E plus, I will not have time to explain. But this immediately gives us the second step, because now it's just a matter of unfolding definitions to see that the limit of the Lyapunov exponent of mu n, which is the limit of this quantity, is going to be, well, it's going to be the limit of the integral with respect to this measure of the function log of the restriction of df to a direction. So this is going to be, by this formula, 1 minus beta times the integral over the graph of E plus of this function with respect to mu hat plus, which is the lift of the limit to the graph of E plus. And when you unfold definitions, you just get 1 minus beta times lambda plus. So this is where the second step comes. Now we come to the third step, which is the main step of the proof, the difficult step of the proof, which is to get an upper bound for the entropy. So let me explain to you the connection between neutral blocks and entropy. So there are several standard ways for estimating the metric entropy of a measure from the behavior of its orbits. And the most classical one is Katoch's entropy formula, which says that if you have a continuous map on a compact metric space, then you can bound the entropy of a measure by the exponential rate of growth of the cardinality of collections of n epsilon balls whose union has measured at least 1/2. You can also take 1/5, doesn't matter. Okay, so again, you take the smallest collection of n epsilon balls whose union has measured bigger than some threshold. The exponential rate of growth of this is an upper bound for the entropy. Now notice that because we're working in a surface, this amounts for calculating the measure of unions of two-dimensional sets. You can do a little bit better if you have more smoothness. If you have C2, then Le Drapier-Young theory in a very rudimentary form tells you that instead of covering a two-dimensional subset of measure at least 1/2, you can cover a one-dimensional subset of a given unstable manifold up to conditional measure 1/2. So instead of working with covers of a two-dimensional set, we can work with covers of a one-dimensional set, an unstable leaf. Again, the covers are by n epsilon balls, which are two-dimensional themselves. But if you have even more smoothness, C infinity, then you can use Yomdin theory to work with covers of the one-dimensional unstable manifold by one-dimensional pieces of the unstable manifold. More precisely, one-dimensional parametrized pieces with small CR norm. And this uses Yomdin theory, and I would like to explain this. I would like to explain exactly what I mean by this. So what is Yomdin theory all about? Well, the basis of Yomdin theory is a definition for the size of a CR curve. So the definition is the following. Suppose you have a curve which has R derivatives, R continuous derivatives. What is the CR size of this curve? It's the smallest number of CR curves modeled on the unit interval with CR norm less than or equal to 1, which are needed to cover it. Now, what's the idea behind this definition? Examine this picture here, this curve here. Look at the bends. At the bends, the derivative the direction of the derivative changes a lot. So no matter how you try to reparameterize this part of the curve, you will have a big second derivative because the first derivative, the direction changes. And the second derivative must allow such dramatic changes. So the only way to get reparameterizations which have small CR norm is to dissect the part close to the bends into very, very small pieces. So small that the first derivative doesn't change much in each small piece, okay? And then you reparameterize each of these small pieces, modeling on the unit interval. And then, because time is slowed down considerably, you have a chance of obtaining reparameterizations with small CR norm. So this is a general principle. If you have a CR object where at some point the slope changes a lot, or the curvature changes a lot, or some case derivative changes a lot, then it will have large CR size, because at this point, to obtain reparameterizations with CR norm less than 1, you will need to chop a lot. Okay, so this is the idea behind the Yomdin theory. So now, how do you use this to get an estimate for entropy? Well, basically, this is a classical work already in the work of Yomdin and developed by Newhouse, and we are going to use Newhouse and Le Drapier-Young. So here it is. Imagine that you have a surface diffeomorphism, at least C2, and you have an ergodic invariant hyperbolic measure. And let's look at one local unstable manifold with its conditional measure. Then you can bound the entropy of the function by above by the exponential rate of growth of collections of parameterized pieces of the curve, which cover the unstable manifold, or maybe even just 1/2 of the unstable manifold with respect to the conditional measure. And each of these pieces must satisfy the condition that its iterates remain small in CR size, in CR norm. Okay, we can relax it a little bit. Maybe not all iterates remain small in CR norm. It's sufficient to ask for some of the iterates, provided they have bounded gaps. Okay, so basically what you need to do is you need to find the cover for the local unstable manifold by families of one-dimensional parameterized pieces of the local unstable manifold, whose iterates has controlled and small CR norm. Now, what exactly does this French condition mean, and why is it connected to entropy? Well, let me show you this in a picture. Imagine for simplicity that the sequence of times are just all times, 0, 1, 2, 3, no gaps at all. Okay, that's a possibility. And let's pick one of those pieces. Then our condition says that sigma I, f of sigma I, f square of sigma I, and so on, they all have CR norm less than or equal to epsilon. If they have CR norm less than or equal to epsilon, then their length has to be less than or equal to epsilon, because the length of a curve is the integral of the norm of its derivative. Okay, and the curves are modeled on the unit interval, and certainly the norm of the first derivative will be less than or equal to epsilon. So each of these pieces has lengths less than epsilon. Now let's pick an arbitrary point inside sigma I and look at its orbit. Okay, because the length of sigma I is less than epsilon, the entire curve is inside an epsilon ball around x. Similarly here, f of x is on this curve. Because the length of this piece is less than 1, the entire curve lies inside an epsilon ball. Similarly for the second iteration and the third iteration and so on. This means that sigma I lies inside an n epsilon ball with center x. So if you have a cover by parameterized pieces which satisfy this bound, then like this, you obtain from it a cover by n epsilon balls. And immediately you connect this family of parameterized pieces to a family of covers by n epsilon balls. So this is the connection to entropy. Okay, so now we come to the proof of the entropy estimate. We want to prove this inequality. And of course, what we need to do, by what I just said, is to construct for each measure mu n, for almost every x, you need to construct a family of parameterizations, Rk, which covers most of the local unstable leaf and whose exponential growth is not too large. What we can get is the main term, 1 minus beta times the entropy, plus an error term. The error term involves 1 over r. R is the degree of smoothness we put into the argument. Eventually, since we are in C infinity, we will be able to take r to infinity. So it will not matter to us. So this is basically how we get the third step. Now, if you give me, Yuri, 3 minutes, I will explain the relation to neutral blocks. Okay, thank you.
I give you even 4.
Yeah, well, that's much better. Okay. So how do we construct these families of parameterization? So imagine, so we start with the local unstable leaf, okay? Maybe the length of this leaf is bigger than epsilon. So we need to dissect it to curves which are short enough so that they have a chance to be reparameterized to have CR size less than epsilon. Now we apply the map. Since it's an unstable leaf, the map stretches the curve. So these pieces that before were short enough to have reparameterizations with small CR norm may now be too long. So we cut them again and we pull back. So we get a finer dissection of our original unstable leaf, and this will be our second family of reparameterizations. Now imagine that after 2 iterations, we get a bend. Bends are very, very interesting in this theory, because in bends, you start getting problems with the second derivative, or maybe with even higher derivatives. So you need to dissect at the bends very finely, and then you pull back. Notice that in parts of the curve, which eventually map to bends, you get very, very fine refinements. Okay? Now, how do neutral blocks enter the picture? Let's examine a piece, a neighborhood on the local unstable manifold of a point which enters a neutral block, and let's see what happens. before you enter a neutral block, you have normal stretching, as predicted by the Lyapunov exponent. And then you can show, basically using Young theory, that the refinements that you get due to stretching grows at an exponential rate of the entropy, or at most the entropy. But what happens when you enter a neutral block? When you enter a neutral block, there is no longer stretching. The curve no longer expands, but it may bend. It certainly can bend. Bends also cause growth in the number of reparameterizations you need. But what is nice is that Yomdin theory gives you very effective bounds for how many bends, how many strong bends can a CR map create in a CR curve. So we use Yomdin theory to control how many refinements we need to do using neutral blocks. And what we find is that whereas the number of refinements we need to do outside neutral blocks grows at an entropic rate because of Young, when you're inside neutral blocks, they grow at the Yomdin rate, which is basically big O of 1 over R, where R is the degree of smoothness. So 1 minus beta times the entropy is the contribution of the parts when you are outside neutral blocks. 1 minus beta gives you the fraction of times you are outside neutral blocks. The big O of 1 over R is the Yomdin theoretic term that tells you the effect of bends and the curvature by iterations of CR maps. So this is how we get this control of the exponential rate of growth of the family of reparameterizations. Of course, in our case, we are C infinity, so at the very end, we can send R to infinity, and this gives us our third and last step of the proof. So to summarize, we defined a number beta, the number of, which is the asymptotic density of neutral blocks. We show that it completely captures the defect in the Lyapunov exponents, defect in continuity in the Lyapunov exponents. We show that it can be used to bound the defect in continuity in the entropy. And when you join these two inequalities, you immediately get this inequality. And this inequality implies our result because it says that if the entropy of mu n converges to the entropy of mu, then this is equal to 1. You get that this is bounded below by 1, it's bounded above by 1 by upper semi-continuity. So this has to be equal to 1. And we get that if the entropy converges, then the Lyapunov exponents converge. And with this, I will finish. So thank you very much.
Okay, thank you, Omri, for this beautiful talk. I'm going to continue with questions, and Enrique, he also made another question, which I think that you kind of answered towards the end of your talk. So he asked, he said the following: Newhouse's theorem is not true in the CR topology when R is finite. What can be said for your theorem in the CR topology? Okay,
very good. That's an excellent question. In the CR topology, there is an additional big O of 1 over R term. It's in fact the Lipschitz constant of, if I remember correctly, it's twice the Lipschitz constant of F divided by R plus 1. So you have an additional term here. It's basically this big O of R. It can be made explicit.
Okay.
So yeah, so that's what happens when you only have CR maps.
Okay. And now Silvio has raised his hand.
Thanks. I just have a small question. I imagine that the fact that you are in the dimension 2 is quite important. It allows you to linearize in the beginning, describe the Lyapunov exponent as a limit of these Birkhoff averages.
Right.
So is this the main technical abstraction to extending to higher dimensions?
Yes.
Linearization. Well, yes. I was going to suggest that, well, there is something called the Avalanche Principle that would, I guess, allow you to obtain this kind of linearization of the description of the Lyapunov exponent in this way, approximately outside of these neutral blocks.
Mm-hmm. Thank you very much for the comment. I don't know what this is, but I will certainly look into it. I'd like to say that when I say that this is the main reason, it's not that we tried and that's where we stuck. The reason I say this is that the other parts of the argument, like Yomdin theory, do generalize to higher dimension. The only thing that seems to be essential to our proof is that the Lyapunov exponent comes from an additive cocycle.
Yeah.
Thank you very much for the comment. I will definitely look into this.
Yeah, the idea is that outside of these neutral blocks, where you have growth, then you can essentially describe the norm of a long block, of a long product of matrices as not exactly a product of the norms. You have some errors in it, but and all of this is quantitative, which could be important in the argument. Yeah.
Okay, thank you very much for the comment.
I think this is also related to Catherine's question on YouTube. She asked, "What about higher dimensions?" So you just you just said what are the main issues?
Yeah,
right?
so we don't know what to do in higher dimensions, because the argument as it's written now depends on the additivity of the cocycle, which gives you the Lyapunov exponent.
Okay, so if you have a decomposition in one-dimensional subbundles, then it works.
I don't know. We were playing at some point with the idea of doing it for three-dimensional flows, but we didn't work on it in a serious way yet.
Okay.
Sorry, I think that you said that entropy is more continuous than Lyapunov exponents. So the other way around is not true. So if you have a continuity of Lyapunov exponents, this implies continuity of entropy. This is not true.
This is not true.
This is not true. Okay.
Yeah.
Even with positive entropy.
No, it's not true.
I see. Okay. Thank you.
Another question from Enrique, he sent to me directly here on WhatsApp. Would it be possible to use Yomdin for measures with zero entropy? For instance, when there is a center manifold with zero Lyapunov exponent and other Lyapunov exponents which are negative? How often do the center manifolds bend?
Definitely, because Yomdin theory applies not just to unstable leaves, it applies to any curve. So basically what it tells you is it gives you what the Yomdin theorem tells you that if you have a CR map and a CR curve, and you look at the image of the curve intersected with the ball of fixed size, it tells you how many parameterizations you need to describe the image, the intersection of the image with the ball. It's not you don't need to assume that the curve is an unstable manifold. It can be any curve. I don't know if this answers what Enrique had in mind, but
I also don't know, but we are going to know soon.
Okay.
I think we have time for one more question if someone wants to make. No? Okay,
There's
so
another question from Henrique Pujals on YouTube. I send it.
So he asked, does it make sense to use Yomdin in the one-dimensional context?
Definitely. The greatest successes have been in the one-dimensional context.
Yeah, there are some works of Jérôme Bouzy, right?
Of Jérôme Bouzy, exactly. Jérôme Bouzy, yes. Yes.
Okay. Okay, so let's thank Omri again for this beautiful talk.
Thank you.